Okay, now we have a Fisher projection here of a monosaccharide, and we're going to try to figure out how many chiral carbons it has. So again, chiral carbons need to have 4 different groups attached to it. So this first carbon has a double bond to an O, and it only has 3 bonds. It's not going to be chiral. This one here, where anytime you see an intersection of lines here, this represents a carbon, and this carbon has an OH and H. It's got this aldehyde group and has all of that attached to it. So those are 4 different groups. That's going to be a chiral carbon. This one over here, same deal. It's got a hydrogen, hydroxide. It's got a whole bunch of stuff over here, a whole bunch of stuff down there, and it's not the same. So that's going to be chiral. This one, hydrogen, hydroxide, whole bunch of stuff, whole bunch of stuff. Yes, there's 4 different groups attached to that one. And then this CH2 has 2 hydrogens, so they're the same. That cannot be a chiral carbon. So I have 3 chiral carbon atoms here. And there we go. How many total stereoisomers are possible for this aldopentose? The way you find that out is you do 2 raised to the number of stereocarbon or chiral carbons that you have. So 2 raised to the third power is 2 times 2 times 2. 2 times 2 is 4 times 2 is 8. So I've got 8 total stereoisomers here. So remember what stereoisomers are? They are going to have the same connectivity. So I'm going to have a carbon, I'm going to have all these same number of carbons, same number of hydrogens, same number of oxygens. And the only thing that's going to differ is what side the OHs are on around those chiral carbons. That's it. We're going to move them around. If they are the mirror images, the two stereoisomers are mirror images of each other, then we call them enantiomers. If they're not mirror images of each other, then they're going to be diastereomers. So we're looking at non-superimposable mirror images. Those are enantiomers. And if they are not mirror images, then they're called diastereomers. So we'll look at all those again. So the next thing they want us to do here in part C is draw and name an enantiomer, the enantiomer of D-lysose. So I'm going to draw a little line there that's going to represent my mirror. And now I'm going to attempt to draw the mirror image. I'm going to zoom in a little leeway here. All right, so I'm going to have a C double bond O on top. I'll make the hydrogen go this way. And I'm just going to draw like what would be in the mirror for this. So if I see that the hydroxides, I have one on the left, left, right. I'm going to do the opposite over here. I'm going to put it on the right and on the right, and then I'm going to put it on the left. The OH on that side. On the other sides, I'm just going to have hydrogens. And on the bottom, I still have that CH2 OH. That's not a chiral carbon, so I can flip that around any way I want. So that would be the mirror image. This one is D because the hydroxide at the bottom, the hydroxide on the chiral carbon that's furthest away from the aldehyde. So if you we're always going to write the Fisher projection the same way. We put the aldehyde on top, and then the hydroxide all the way at the bottom here. This one has to be attached to a chiral carbon. If that's on the right side, we call that D. If it's on the left side, we'll call that L. So this one over here is going to be L lysose. L lysose. So just because the OH group is on the left. All right. The next one, it says D-ribose is a diastereomer of lysose. Can you draw 2 additional D-diastereomers of this monosaccharide? Okay, so D just means that there are 8 total. There are 8 total. We've just stereoisomers. We just drew 2 of them. There are 6 more. They're just asking you to draw 2 of those, and they want specifically the D diastereomers. Okay, so what does that mean? Let's give ourselves a little more room here, and we are going to draw 2 more of these. All right, so I'm going to set this up like this, and I'm going to put my aldehyde on top. That's not going to change. The only thing that's really going to change here is where I'm putting these hydroxides. All right, so in lysose I have it as left, left, right. Since they're asking us to do the D isomers, I know that I have to have the hydroxide on that last carbon over here. And so now I can just play around. If I put them both over here, then that's the D lysose. That's not what I want. So maybe I'll put one over here and one over here. That might work. And then what if I flip that around and I did one over here and one over here? There we go. Put in my hydrogens. The other one is ribose. Ribose is when they're all on the same side. So ribose would look like, they didn't ask you to draw this. You don't have to draw this. Just wanted to show you. Yeah, the ribose. It's going to look like that. And then each one of these D's is going to have an L that goes with it. And all you would do is draw the mirror image of it. There, that one's ribose. And so these are the other two that we drew. These are hydrogens. Oh, and I lost my CH2OH. There we go. So the only thing that's different about them is really the orientation of that OH in space. Where are we putting those OHs?